Continuing on with our discussion of BGP here, we talked about the general attributes of the protocol. What are the different requirements for establishing the peerings, whether they're IBGP or EBGP, and some of the different attributes that are going to apply in the differences of those type of peerings. So next we're going to take a look at the command line, go through some examples of actually establishing the peerings, look at the different verifications with the show commands and debug commands to figure out what are the potential problem issues that we could run into when we're actually trying to establish the adjacencies. Now again, the key point in our first step when we're defining the neighbors to actually establish the BGP peering is that this command has dual functionality. It means that we're going to start listening for a BGP connection to come from the remote address, and also that we are going to initiate a session that is going to the remote address. With these two attributes, both the TCP client and the TCP server have to agree on where the BGP session is going and where the BGP session is coming from. So let's take a look at our topology here, where internal to the network, right now I have everyone running IGP, where EBGP AS100 is running on all of the transit links and advertising their loopback interfaces into the topology. So at this point, if we were to look at anyone in the network, let's say switch 4, for example, and look at the show IP route, we should see essentially any destination that is internal to our network, we should have reachability to it. So the loopback interface of router 1, of 150.28.1.1, of router 2, of router 3, etc. So the first requirement of BGP is that we always have that underlying IGP transport. If we cannot establish basic IGP reachability, then it implies we cannot establish the TCP session, and we can't do any of our other options beyond that in BGP. So first, let's look at doing some peerings between directly connected neighbors. We'll look at establishing a session between router 4 and router 5, where they're going to be in separate autonomous systems. So we'll say that router 5 is simply in AS5, router 4 is in AS4. At this point, we have two directly connected interfaces between them. One of them is the frame relay interface, one of them is this point-to-point link. So if we were to look at router 4 and look at the show IP route connected, the two links between them are 155.28.0, where router 5 is .5, and the 45 network, where router 5 is also .5. So before we actually enable the BGP process, I'm going to turn a couple different debugs on here. One of them is going to be to look at the actual BGP peering messages, and the other one is a low-level debug for the actual IP transport. If we look at the show IP protocols, right now I'm using EBGP AS100 as the IGP for transport. Now what I'm going to do here to look at the BGP packet formats but not get the EBGP ones in the way, when I do the debug, I'm going to filter to specify I do not want to debug EBGP. I essentially only want to debug the BGP packets. So to do this, I'm going to create an extended access list. I'll say access list 100 is going to deny EBGP and then permit anything else. So this would be any other IP protocol number, whether it's ICMP or TCP or UDP. This access list is going to match it, as long as it's not protocol number 88, which is EBGP. Then we're going to look at the debug IP packet detail, but filter this through access list 100. So now in this output, we should not see any of our EBGP hellos or any of our actual EBGP updates. But if I were to send a ping to router 5, we should see this output in the debug because this is not protocol 88. Now you can see with just those 5 pings, debug IP packet detail is going to generate a lot of information. So normally if you're going to look at this debug, you would not want to send it to the console. You would want to send it either to the log buffer or to like a remote syslog server. But in our case, since I know there's not a lot of traffic in the network to begin with, then we're just going to look at these from the console. Now, also to make the debug a little bit clearer, I'm going to remove the timestamping from all the routers, because that's going to take up a bunch of the lines in the output. So from the access server, I'll send to all the routers no service timestamps, which is going to affect the debug messages that are coming up. So now again on router 4, if I were to send a ping to router 5, and let's say just one packet, we can see even just for one packet, since we're looking at the detailed debug, it's a lot of information that's coming up with the output. Now, in addition to this, we're going to look at the debug IPBGP, which essentially is all of the debugs for that particular address family, which is IP version 4 unicast. Now, the difference in the address families, we'll talk about that in a little bit later sections when we get to multicast, IPv6 routing, and then also for MPLS routing. Now, we can see from the output on router 4 here that there were some packets received in from the address 204.12.28.254. It says that the packet was TCP. The source port was 16,119, destination port was 179, and the type of packet was a SYN. Now we know TCP 179 is BGP, so what this essentially means is that there's some neighbor on our connected link, which in this case is BB3, that's trying to establish a BGP peering with us. Now, since I don't have the BGP process configured, when the BB3 sends those requests to start the TCP session, router 4 is going to reply back with a reset. It's saying that either I'm not running BGP, or I don't have a particular peering that is associated with your address. Now, if we were to configure a neighbor statement under the BGP process for that particular address, 204.12.28.254, then router 4 would be listening for the session. But the key point is that by default, BGP is not dynamic in the term that it cannot learn its peers automatically. We have to specify these manually with the neighbor statement. So next, under global config, we'll start the BGP process. We'll say this is BGP AS4. And we could also see, based on the iOS version of router 4, it does support the 4-byte autonomous system. So we'll come back to that a little bit later and see what happens when we have the 4-byte AS plus the 2-byte AS interacting with each other in the topology. Now, before I actually configure the peering, I'm going to go to router 5 and debug IPBGP, and then do the same access list debug where I'm denying EBGP and then permitting everything else. So access list 100, permit IP any. After the deny EBGP, then I'll debug IP packet detail using access list 100. Now on router 4, I'm going to specify the neighbor statement that's going to, let's say, the frame relay interface of router 5, so 155.28.0.5, and router 5 is going to be in autonomous system number 5. If we now look at router 5, we should see that there is a TCP SYN packet coming in from router 4. It's going to port 179. This is router 4 trying to start the session. Since router 5 does not have the neighbor statement configured on the way back, it's replying with the reset saying, I don't have this session configured, which is what we'd expect because router 5 is not configured for BGP yet. So now let's go into the process. We'll say router BGP 5, and router 5 is going to peer with router 4, but in this case we're going to peer with the point-to-point interface, not the frame relay. So the remote AS is 4. So in this type of case, what we would see, where router 4 is configured to peer with 5 via the frame relay, and 5 is configured to peer with router 4 via the point-to-point link, since the TCP server and the TCP client do not agree on where the session is coming from and going to, when the initial BGP open message is sent, the other neighbor is going to reset the connection. And we see this from router 5's output that I tried to send from myself going to port 179 the first portion of the three-way handshake. So I'm trying to open the TCP session. Then router 4 replies back with a TCP reset saying I don't have a peering configured for that particular address, which is the 45.5 address. If we look at it in the reverse path, likewise router 4 via the frame relay is trying to initiate the session to 5. Then router 5 is resetting this saying that I don't have a peer that is configured for that particular address. So this is why it's very important in the BGP network to figure out what is the route between the two neighbors before we go to establish the peering. Now between these two routers, it's pretty obvious to tell what it is because they're directly connected on both of those links. We know that if router 4 is going to route to router 5's frame relay interface, router 4 is going to use this connected link to get there. Then likewise on router 5, if I'm going to get to the address of serial 0/1/0 on router 4, I'm going to use my local interface to get there, simply because those are connected routes. Now where this is a little less obvious is where the routers are more than one hop away from each other. Then it is going to depend on the routing table to determine whether the session will or will not be allowed. So now let's say, for example, that router 5 is trying to peer with router 6. And router 6 is in AS6, router 5 is in AS5. So this is a multi-hop EBGP peering. When router 5 configures the neighbor statement, let's say that we point it at the VLAN 67 interface. When router 6 configures the neighbor statement, it points it at the point-to-point link to router 5. So now we would need to consider when router 5 generates the TCP packet to begin with that is going to router 6, what is the local interface that I would use in order to reach that particular destination? Now we can tell this on router 5 if we were to look at the routing table. If I were to say show IP route for 155.28.67.6, it says my particular route to that destination is via serial 0/0/0. Now this essentially means that whatever IP address I have assigned on that interface, that's going to be the source of the packet when it goes out to router 6. Now on router 6, we can't necessarily guarantee that the return path is going to be the same via that interface. So if we look at the show IP route for 155.28.45.5 or the 0.5, notice that for both of these addresses on router 5, router 6 says that I would use fast Ethernet 0/0.146 in order to get there. So from router 6's perspective, if we were to look at the show run interface fast Ethernet 0/0.146, each BGP update is going to come from the address 155.28.146.6. If this does not match with the neighbor statement that router 5 has configured, the TCP session will not establish. And you could think of this as kind of a security mechanism for BGP, where essentially the two neighbors, they should already know what addresses they're going to peer with. If someone is trying to spoof the BGP connection, maybe they're sending the setup message to some random address on the router, we would ideally want to deny that connection. So BGP does not run in promiscuous mode by default like OSPF or EBGP does. Now there's a simple way that we could get around this design issue, is simply to tell the routers what is the address we want to use when we're sending packets to that neighbor. And this is what the update source command is designed to do. So in any situation that we are not peering over a directly connected link between the neighbors, we should manually specify where the packet is coming from, so the remote end is then going to agree with that. You'll see that the vast majority of real design cases for this will be that the update source is going to be a loopback interface. The reasoning behind this is, let's say between router 5 and router 6, if I'm advertising my loopback into IGP, then it really doesn't matter what physical link I'm using to route in order to get between router 5 and router 6. As long as there is one physical path available, then I should be able to reach from 6 the loopback of 5, and from 5 the loopback of 6. So as long as they're both agreeing on the TCP session, it doesn't actually matter the path that the control plane traffic is routed. As long as it gets to them and the TTL is not expired in the transit path, that's really all that we care about. Now for the peering between router 4 and router 5, we could manually change this on router 5 to say that to get to that address, the serial 0/1/0, the update source would be the frame relay. In that case, we would see that at least in one direction of the session, the client agrees with the server as to what the address is, but typically you wouldn't want to do this implementation. It's kind of overcomplicating the issue. So what I mean by this, I could go to router 5, and under the BGP process, we'll say that for this particular neighbor, my update source is serial 0/0/0. Now if we were to look at router 4 and look at the output from the debug, we're going to see both the IP packet debug and the actual BGP peering state machine output, where router 4 is saying that I sent a packet. Let's see, let's scroll up a little bit further. It's going to be right here as the start of the session. So it says a packet came in from router 5. It's going to one of my addresses. Now from router 4's perspective, it doesn't really care where the packet is going. It's more concerned about where the packet came from. So the packet came from 0.5, which matches one of the neighbor statements that I have configured. We see that this is going to port 179, so it means that router 5 here is the client, because the client's communication is going to 179, where the server's communication is going to be sourced from 179. So we see the reply from router 4, it's coming from 179 going back to router 5. This is the second portion of the handshake. Router 4 is acknowledging 5, I got your packet, sending to SYN saying I also want to open the session. Then we should see the final portion that is completely opening the session, which is router 5's acknowledgement to router 4, saying we're going to start a TCP session on port 179, and this is the particular random port that we're using, 52798. So we see once we get past the actual TCP transport establishment, then we actually go through the BGP state machine, where it says that now we're trying to connect. We received an open message from router 5. This is where the routers go to the actual negotiation of what are the options for the adjacency. So router 5 is saying I'm running BGP version 4. This is the whole time that I want to have configured. Then it says we are negotiating a capability, which is for address family identifier 1 and sub-address family identifier 1, which essentially is IP version 4 unicast routing. So router 4 is telling router 5, and they're agreeing on this, that both of them want to run regular IP routing, which is going to be the default. Okay, we'll also see some of these optional capabilities that are there by default. The route refresh, which we'll see later is used to ask for or send triggered updates in BGP without having to destroy the TCP session and then rebuild the full adjacency. We'll also see there's some other capabilities they negotiated here. One is going to be the 4-byte autonomous system number. Then we go from open send to open confirm, basically saying that I agree with whatever options that you wanted. So here, before we get to open confirm, this is where we could potentially see a misnegotiation in the parameters. So if router 5 was trying to run IPv6 routing, where the other router is trying to run version 4 routing, then instead of going to open confirm, we would see a notification message being generated. So notification means that they could not exchange a set of capabilities where they both agreed on, and they're having to reset the session. So it could be something as simple as the AS number is wrong, or you're trying to route IPv6 while I'm trying to route IPv4. Okay, then we actually go to the normal data exchange. This is where we're sending the update messages. Okay, at this point, we're not actually advertising anything into BGP. So eventually, we'll see that the session goes to fully established, which is here. So if we're not doing any debugs, once the peering is working, we should get this final log message that says BGP5 adjacency change, the neighbor is up. Okay, not that we're running BGP version 5, just that this is a level 5 logging message. So if we were logging level 5 or above, then we should see this particular log. So if we look at the configurations on both of them, let's say show run section router BGP. We technically can do this configuration where they're peering with different physical interfaces. So router 5 is peering with 4's point-to-point serial, but it's sending its updates from the frame relay. As long as router 4 agrees that this is where the session is supposed to come from, then the peering is going to work. Now, what would be the disadvantage of this type of design? Where router 5 is peering with the point-to-point link, 4 is peering with the frame relay, and router 5 is sourcing its updates from the frame relay. The problem is going to be that if either of these physical links goes down, then the BGP control plane is going to be lost. So even though there may be multiple routes between the neighbors, BGP would not be able to take advantage of that if the peering is based on a physical interface that has the IP address assigned. So in the vast majority of cases, you'll see that if the BGP peers have multiple IGP routes between them, or multiple IGP paths between them, then it would make more sense to source the connection from the loopback interface. So let's undo the neighbor relationship we have here. So on router 4, let's just say no router BGP 4. And on router 5, we'll say no router BGP 5. Okay, we'll look at those same debugs though. We'll debug IP packet detail 100 and debug IP BGP. Next on router 5, we're going to start the process again. I'm going to configure a peering with the loopback address of router 4, which is 150.28.4.4. We'll say they are in AS number 4. And I am going to source my packets from my own loopback 0 interface. Then router 4 likewise is going to do the same thing. So router BGP 4, I'm peering with router 5's loopback. And my update source is loopback 0. We debug IP packet detail 100 and debug IP BGP. Now, before we can establish the TCP session, we're assuming here that there is reachability between those two loopbacks. So it may make sense to test this if we ping 150.28.5.5 and source this from my own loopback 0. I know that there is transport between the two addresses. Okay, we see the debug IP packet output is a lot, but there was a correct response in from the ICMPs. Okay, so we see there's the echo reply coming back from router 5. If we look at the debug output on router 5, though, we'll see that there's nothing here that is related to the BGP session either trying to be established from router 5 or being sent to router 5. The reason why is that since these are EBGP peers, router 5 is going to say, what is my route to get to 150.28.4.4? Since this destination is an EBGP peer, and the route is not via a connected interface, so I'm learning it via IGP, I'm not learning it via connected link, then neither of the processes are going to establish by default. So essentially no one is going to send the initial TCP SYN. This is what the neighbor disable connected check would be for. Disable connected check. So technically router 4 and router 5, they are not more than one hop away. Because if we were to do a trace route to 150.28.4.4, we see it's only one hop away. So regardless which interface we go out, whether it's the point-to-point link or the frame relay, it's only one hop away. But router 5 right now has been configured to disable that connected check, where router 4 has not. So router 4 is receiving the packet in. It's saying to get to you, you're not via a connected interface. So I'm sending a TCP reset instead of agreeing on the session. So essentially both of the neighbors would have to agree on this. If we say under the BGP process that for this neighbor, we want to disable the connected check. So we see we go through the full capability exchange, now the neighbor's up. If we now look at the output of the show IPBGP neighbor, this is going to give us all the detail about that particular peering. So to start, it says this is the neighbor's address that I'm actually peering with. We're both running BGP version 4. The router ID of them is 150.28.5.5. Now we'll see later, both in the BGP best path selection and some of the loop prevention mechanisms, BGP will be using the router ID to figure out if an update was locally originated from that local device. Next it says that the hold time is 180 seconds, the keep alive interval is 60 seconds. So this is basically like the hello and dead timer for OSPF. Now with BGP, this value does not have to match in the configuration. It will be automatically negotiated down to whatever the lower value is that the neighbor is requesting. So on router 4, if I were to set the timer values lower, let's say 5 seconds for keep alive and 15 seconds for the hold time, if I were then to clear the TCP session and do a new reestablishment of the peering, then we would see that both of them are going to use those lower negotiated value. Next it says the neighbor capabilities. We have route refresh advertised and received. We'll see later again this is going to be used for sending and requesting triggered updates. The new autonomous system number capability, that's going to be for the 4-byte AS number. Address family IPv4 unicast. So this means we're running normal IP routing over this session. If we were running IPv6 or IPv4 multicast or MPLS, we should see under the neighbor capabilities that they have both advertised and received that particular attribute. If it says IPv6 is advertised but not received, it means they're not both agreeing that they're going to run that particular type of routing. So most of the rest of the output here will be things that you shouldn't need to reference most of the time. Things about the statistics of how many prefixes are being advertised, withdrawn, how many are being used for the best paths. One other thing we may want to know is what is the time to live, who is the server, and who is the client. So from router 4's perspective, it is the server because it is sourcing its traffic from 179, and the traffic is going to 47.909. If we were to look at this on router 5, it should be the opposite. Router 5, if we show IPBGP neighbor, router 5 says the local port is that random one, 47.909. The foreign port, or the remote port, the destination port, is 179. Now, in reality, it's not going to matter who is the client and who is the server, as long as there's no filtering on port 179. The actual device that becomes the client is generally just the person who initiates the session first. It's only going to go to the router ID if both of them happen to send the TCP SYN at the same exact time. So you could technically run into some advanced designs where maybe one router is behind network address translation. Then it would matter who is the client and who is the server if an outbound connection is allowed, but an unsolicited inbound connection is not. So that would be the same like if we're going through some sort of active firewall. There's a question, what is the incoming TTL here? That's actually going to be related to the next feature that we're going to look at, which is the TTL security feature for BGP. Now, as we know, the peering between these two neighbors is EBGP, so it means the time to live is 1 between them by default. Now, let's say that I were to do a peering between router 5 and router 6. So router 6, we'll say it's an AS6, 4 is in 4, 5 is in 5. So from 6 and 5's perspective, they're going to be multiple hops away, which is fine as long as we tell the routers that you need to increase the time to live for that particular session. So let's go to router 5, and under the BGP process, we'll say neighbor 150.28.6.6, remote AS6. My update source is loopback 0, and I need to increase the time to live. So EBGP multihop, and I could give it a value, or I could just use the default, which is 255. Okay, if we do not configure this command, it defaults to 1. So by specifying EBGP multihop, when we look at the running config, show run section router BGP, it says now the time to live has changed to 255. So it essentially means it doesn't matter how far away they are, as long as I can reach them, I'll establish the session. Now on router 6, we're basically going to do the same thing, but it's going to be on the reverse path. Now you'll see with a lot of these BGP configs, since the syntax is fairly similar, where the only main difference is that we're changing the addresses, a lot of times it makes sense just to do these configs in Notepad. This will also make sure that you're not leaving some sort of key configuration out, like the update source on one side, or the multihop, or whatever other attributes that we want. So on router 6, I'll paste this same configuration in, where the only thing that has changed is the local autonomous system number, the remote AS number of router 5, and then the loopback address of router 5. From router 6, if we now look at the show IPBGP neighbor, it says that the neighbor is an external BGP neighbor that may be up to 255 hops away. So this is the outgoing time to live. Now, by default, the EBGP multihop command is only going to control what the TTL value is on your outbound packets. So technically, router 5 and router 6, they could have different multihop values as long as the packet eventually gets there. Now, the potential design issue that we could run into, though, is that it is possible to spoof a TCP session if you have some sort of attack that can predict the TCP sequence numbers. And originally it was thought that predicting the sequence numbers was not feasible, but some of the attacks fairly recently have shown that it is possible to do that. And there are attacks that you can use to actually reset a TCP session of BGP on the internet. Now, what the implication of that is that if I send TCP reset attacks to the transit routers in the internet, they're going to drop their BGP session and then start dropping all traffic. So it's against essentially just a control plane denial of service attack, where we're trying to tell the router to delete its BGP peerings, which then means it has no routes. So to protect against this, if router 5 and router 6, let's assume that they are exactly 2 hops away from each other. So we know that there's only one router between them. So when router 5 sends a packet to 4, 4 sends it to 5, or 4 sends it to 6, when 6 receives the packet in, we could infer the transit path that the packet followed if the time to live value is 255 minus the number of hops. So if this device is supposed to be 2 hops away, and we say that the TTL should be at least 253, this would prevent a case where router 6 connects to router 3, and then we go out to the rest of the IP cloud. It would prevent an unsolicited attack from coming from someone who is more than 2 hops away. So if we're assuming that this TCP reset attack is going to come from some end host in the internet, it's very likely that they're going to be more than 2 hops away from this particular router. So maybe when the packet finally gets to router 6 from the attacker, maybe the TTL is like 228. So router 6 can implement a check that says when I receive the BGP packet in from this neighbor, check the remaining time to live. If it is below a certain threshold, it's possible that that session is trying to be spoofed, so I'm simply going to deny that packet. Now, there's a question here, doesn't the password already protect against this? Technically, it does, because for BGP authentication, it doesn't use its own form of authentication. Okay, it uses what is defined in TCP option number 19, which is the MD5 signature. And this is defined by RFC 2385. Okay, it says it's a TCP extension to enhance BGP security. So it's essentially just a password that is MD5 hashed between the neighbors. The problem with this, though, is that every time the router receives a packet in, it has to run an MD5 hash on the header. So if we were trying to implement some sort of reset attack, it's not going to work. Let's say the attacker is here. So the attacker is here. They're connected to the IP cloud. They're multiple hops away from router 6. If router 6 is doing authentication with router 5, then there's no way that they could do a reset attack. But they can technically do a denial of service attack against the MD5 process itself. So if we figure that the attacker is sending however many packets per second it can, let's say it's sending 20,000 packets per second, okay, which is a fairly feasible value that you could be able to forward into the internet. If I'm sending 20,000 malformed TCP SYN packets per second, it means that every time router 6 receives those, it's going to have to run the MD5 hash against it. So it's essentially a denial of service against the control plane that's not trying to get them to drop the routes. It's just trying to get their CPU so high that they can't even manage the session to begin with. So typically you would implement both of these at the same time, the password authentication plus the TTL security. So then the router says that if the TTL is lower than the threshold, I'm not even going to look at the password. But if the TTL passes the threshold and the password is correct, then I will allow the packet in. But the key thing that's good about the BGP authentication is since BGP is already running on top of TCP, there's no need to define a separate BGP authentication. It can just use the underlying option number 19, which is already part of TCP. So there's a lot of research that's been done on these type of attacks. I believe one is, if you search for BGP reset attack, and I think it's called slipping the window. This is basically a proof of concept that someone did on it's actually feasible to get this attack to work based on some algorithm they came up with to predict the TCP sequence numbers. And they give the time that it takes to do that. And in certain cases, you could have the attacking application figure out within like 10 to 15 minutes or so what the value is supposed to be, and then the session drops. So ideally, you want the router to protect against this type of attack to begin with, so then you never have to worry about something like the TCP sequence numbers. So configuration-wise, if we were to look at the command reference for BGP, this is going to be under the neighbor options. Then it would be the neighbor, actually the next one, neighbor timers through show BGP. It's neighbor TTL security. So it says neighbor TTL security provides a lightweight security mechanism for BGP to protect against utilization-based attacks. Configuration-wise, you specify for the neighbor what the minimum hop count should be, or actually the minimum TTL what it should be when the packets come inbound. So for example, if router 5 and router 6 are supposed to be 2 hops away, then this is what the argument is going to be of the command. So it actually means the reverse of that. They're going to look for 255 minus those hops to figure out if that particular session is valid. Now, if you look at the specific usage guidelines here, it says that the TTL security and the EBGP multihop, these commands are mutually exclusive. So you do one or the other, not both of them at the same time. But the key for this to work is that you'd have to do this on both sides. So if you're setting up a new BGP peering with your service provider, it makes sense to try to negotiate this capability with them. So even if they're only 1 hop away, even if the neighbors are directly connected, it's still feasible that someone could do a TCP reset attack against the BGP router itself. So implementation-wise, this is really, really simple. If we were to go to router 6, and let's do a trace route to figure out how do I get to the loopback of 5. 150.28.5.5. It says I either go to router 1 or to 4 and then to 5. So in either case, regardless of whether I'm going to 1 or 4, it's going to be no more than 2 hops away. Then likewise on router 5, if I were to trace 150.28.6.6, says I could go to routers 1, 4, or the point-to-point link to 4, then I'm going to go to 6. So there's multiple routes that are being equally load balanced between, but as a whole, it's still no more than 2 hops away. So now under the BGP process, I would say for this neighbor, I don't want to have multi-hop. And actually, let's leave it on. Let's see if it generates a log message. We'll say TTL security, the number of hops, they're no more than 2 hops away. Okay, and it does generate the error message there. It says remove EBGP multi-hop before we do TTL security. So let's take this one off. Then we'll do the same thing on router 6's side. So under BGP 6, no neighbor 150.28.5.5 EBGP multi-hop. And instead, we want TTL security, and the number of hops should be no more than 2. So now if we clear the BGP neighbor, we should see that the session for router 5 goes down, and then eventually it comes back up. If we look at the show IP BGP neighbor, 150.28.5.5, we should see now that it says that the neighbor could be up to 2 hops away, but the minimum incoming TTL has to be no lower than 253. Because if they're 2 hops away, we know that they're using 255, because that's what the feature does to begin with. So 255 minus 2 hops away, it means that it should be no lower than 253. So if the packet comes in and it's 252, it's going to be denied. Now we can actually test this. If I were to go to router 6, and let's say I change the path to get to router 5, and we could just do this with a manual static route. So I say to get to router 5's loopback, I'm not going to go towards router 4 or 1. So normally router 6 is going this way, to 4 and then to 5, or to 1 and then to 5. Let's say that I force the traffic to reroute in this direction. So now it would be at least 1, 2, 3 hops away. So on router 6, we're going to route this packet towards switch 1. Then if we trace 150.28.5.5, actually now switch 1 is not agreeing on that. So instead of doing the static route, I could change the EBGP path selection. So let's say the delay on that fast Ethernet link is really high. Then we clear IP EBGP neighbors. So ideally, router 6 should now change its path selection so that we go to a different route, and now we can see it's 3 hops away. So on router 5, if we look at the debug IP packet detail 100 and debug IP BGP, then clear the neighbor, clear IP BGP 150.28.6.6. And I'm not sure if it's going to show a specific error message here. It says packet routing failed. So let's undebug this. Let's look at the show IPBGP summary now. So I think it just silently discards the packet. So nothing has really changed in the configuration other than the route that we're using to get there. So we're still able to reach router 6 when the traffic is sourced from my loopback 0. So they are only 2 hops away from my perspective. But now when 6 does the trace to 5, it's more than 2 hops away. So now this one is being denied. So the only disadvantage of this is that if the remote device is actually more than 2 hops away, sometimes it could be hard to predict what's the actual route that they're going to use between them. So in a real design, it would be more realistic to use this type of feature between router 4 and router 5 directly. So even if there's only one path between them, it would still make sense to do it. So if 4 and 5 are peering over this connected link, they would say the number of hops is 1. So then there's never a valid case where 5 would receive a packet spoofed from router 4's address that's trying to reset the session, or that's trying to do some sort of update injection, for example. But again, this is really going to depend on whether that particular version that you're using is going to support it. So if we look at this command, it says that this was integrated as of 12.3.17. So pretty much any fairly recent version is going to support this. And this would then be the better design choice to use. Instead of EBGP multihop, you would want to use the neighbor TTL security.